2.5, so we've got that covered. And so here we go. This is the last bit of topic that we have for this unit. Okay. And let me just start off by saying that in section 2.4, our problems looked like this. We looked at the limit as x approaches a of f of x, and we said, we looked at the instances where this came out to be either arbitrarily large positive or arbitrarily large negative. Okay? I've tried to keep section 2.4 and 2.5 separate so you had enough time to absorb 2.4 prior to moving into 2.5. Okay. What's critical that you understand here is what is approaching a finite number in this problem?
Y?
No? Not y. A finite number. A fixed number.
Oh, X.
Yeah. So what's going on here? As the domain values approach A, the range values does what? Gets large. Okay? It's critical that when you're looking at this limit notation that you're able to see where are the domain values going, where are the range values going, and keeping track of those. Okay? Because here in 2.5, we're going to look at the limit as x approaches infinity of f of x, and we're going to say that that's something like L in some cases. Not always, but in some cases. So what's going on here? As the domain values do what? They get what in this problem?
Large.
They get large. As the domain values get large, do the range values approach some number L? Okay? So this is how you've got to keep track of these two different types of issues. Okay? Because we use different techniques in different types of problems. All right. So that's actually the summary of this entire lesson. Okay? But let's actually jump into it. Here I want to look at the graph of this function right here. F of x equals x squared minus 1, all divided by x squared plus 1. Okay? First of all, let's ask this question. Does this function have any vertical asymptotes or holes? Peyton, you're shaking your head.
No. X squared equal -1.
Yeah. What's the domain of this? What's the domain of this function? What am I allowed to plug into this function? The domain of this function goes from minus infinity to infinity, right? There is nothing, because the only operation that could potentially get me into trouble is what? What operation? Multiplication, addition, square rooting. What am I doing that could get me into trouble?
Division.
We're dividing. So I've got to make sure I don't divide by what? 0. What would make the denominator 0? Ah, okay. If x squared came out to be -1, but what number when you square it gives you a negative? No real number. Okay? So there is no number that would make the denominator in this expression 0. Okay? And so let's just do a couple of things. What is f of 0? Let's find the y-intercept. The y-intercept is -1. Everyone okay with that? Okay. Let's find the zeros of this thing. How do you find the zeros of a function? You set the function equal to 0, right? Well, that happens when x squared minus 1 over x squared plus 1 equals 0. What is the kind of the general form of the expression on the left there? It's a fraction, right? When is a fraction 0?
When the numerator equals 0.
When its numerator is 0, right? So that happens when x equals plus or minus 1. That's when the numerator is 0. Okay. So putting that information in here, okay, here's the y-intercept of 0, 1. Here are the x-intercepts, the zeros of the function at -1 and 1. This has no vertical asymptotes or holes. Okay. Here's a question for you. What happens when I plug 10 into this function? What do I get out? Let's actually evaluate that. What do I get out when I plug 10 into this function?
99/101.
Yeah, if we plug in 10, we square it, we get 100. Minus 1, we get 99. If we plug in 10 into the denominator, square it, we get 100. Plus 1, that's all over 101. How are we doing, folks? What's that number close to? 99 over 101, what's that close to? close to 1. And in fact, if I plugged in 1,000, I'd get something what? Even closer to 1. Okay? So the graph of this function looks something like this. So what I want to talk about now is what we call the long-term behavior of the graph, meaning away from 0. How is this function behaving? Away from 0, how is this function behaving? Well, let's find out. Remember in previous classes we'd say that this has a horizontal asymptote at y equals 1? We want to somehow encapsulate that with limits. We want to use limits to be able to describe this idea. Okay? So here we go. This is what we say. If as x becomes arbitrarily large, f of x gets arbitrarily close to L, meaning as x approaches infinity, f of x approaches L. How do we write that in limit notation? We will write the limit as x approaches infinity of f of x equals L. Okay. In this second statement here, as x becomes arbitrarily large but negative, if as x becomes arbitrarily large and negative, f of x becomes arbitrarily close to L, meaning as x approaches negative infinity, f of x approaches L. How would we write that in notation?
Same thing, but negative infinity.
Same thing, except for our limiting value is going to be negative infinity. Okay? So for f above, by above I mean in number 1. In number 1, what would we write here? Yeah. We'd say as x goes far to the right, as the domain values get large, what do the y values get close to? What do the range values get close to? And we see, as we go further and further to the right on this graph, the y values are getting closer and closer to 1. So how do we encapsulate that with limit notation? Using this expression here. Now this is not truly a limit the way we originally defined limits. Because we originally defined limits for domain values approaching some fixed number here. But this notation is powerful enough to also take on this idea too. Okay? The domain values get large. We find that the y values approach 1. Okay, let's read that together. As the domain values get large, the y values approach 1. All together, one more time. As the domain values get large, the y values approach 1. Okay? Do you see that these limits make a lot more sense if you read them aloud? Does that make sense? So practice doing that. Okay? If you see LIM x arrow infinity f parentheses x close parentheses equals 1, if that's how you're saying that to yourself, you're never going to fully grasp the notation. All right. What do we find here? As the x values go far to the what? To the left, what do the y values appear to also be approaching?
1.
1 as well. Okay. Okay. So if, as x gets large to the right, we approach L, or if, as x gets large to the left, we approach L, or both, then we say that the line y equals L is called a what? Horizontal asymptote. Okay. All right. So go ahead. I'd like you to do number 5. You've got all the tools you need for number 5.